welcome. In this lecture, we shall be learning something more about the basics of the refrigeration and liquefaction. So, in this lecture, we shall be doing some derivations and see that how to read the TS diagram etc. further. So, what we shall learn? We shall learn about the JT expansion coefficient, the expansion of an ideal gas, the JT coefficient for a gas obeying van der Waals equation of state, and isentropic expansion coefficient. So, let us take the first problem. Here we have that we have to derive an expression for the JT expansion coefficient in terms of temperature and the specific volume. This particular expression we have given in our theoretical class. Here we shall be deriving that particular expression. So, in this what we do that we take the first law of thermodynamics and we assume the steady flow through an expansion valve and we make some assumptions. One is that there is no heat transfer, there is no work transfer, and there is negligible changes in the kinetic and potential energies. So, with this, let us first see that if we draw a temperature versus pressure curve, how it will be. So, here we see that there is some fluid that is going, this particular pink volume shows that it is the barrier or the expansion valve you can say, and here we have some fluid, a gas maybe, that it is coming at some pressure P1 and T1 which is fixed, and now it is going through this valve and getting expanded, and here we have some other pressure and temperature, and in this what we are saying that we shall be seeing that the enthalpy is remaining constant. So, with this we shall see that this kind of this line we shall be getting, and if we make it isenthalpic line, then you see that this is the H is constant here, and when H is constant and suppose here we have P1 T1 and suppose here we have P2. Now, we see that here in this case what happens that this H1 is equal to H2 because of these assumptions. So, this is from the first law of thermodynamics, and here we see that these two may be at different places on this isenthalpic curve. Now, depending on where it is, the gas will either undergo a temperature decrease or a temperature increase, and the slope at any point, whatever slope we take, that slope will be this dou T by dou P at constant enthalpy, because we are dealing with a isenthalpic line. So, if we find the slope of at any point, we shall be able to get the value of the this expansion coefficient at constant enthalpy. And now, what we see here is this, that on this zone, in this zone, when we are decreasing the pressure, the temperature is increasing. On the other hand, whenever we are in this zone, so when we are decreasing the pressure, the temperature is also decreasing. So, when the temperature is increasing with decrease in the pressure, now mu Jt as from the definition is coming out to be negative. That means, if this mu Jt is coming to 0, it means that the gas will get heated up on expansion. On the other hand, if we go to the other zone where with a decrease in the pressure the temperature also decreases, this zone we have mu Jt more than 0, that is positive. So, for cooling we want the mu Jt to be always positive. Now, here whenever there is a change in the slope, it is called the point of inflection. So, here this particular point, this is the what we call the point of inversion. So, whatever temperature we read here, this will be the inversion temperature of the particular gas. Now, here we see that in this particular figure there are several isenthalpic lines, and now you will see that if we draw this kind of things for each of the isenthalpic lines and then we join the inversion temperatures. So, we get this particular dashed curve, this is the locus of all the inversion temperatures, and this particular locus is called the inversion curve. So, that is how we generate the inversion curve. So, we see that on the left hand side of the inversion curve we have mu Jt always more than 0, and on the other hand, on the right hand side of this inversion curve, we have mu Jt always less than 0. So, for cooling, we would like to be on the left hand side of this particular curve, and this particular thing, wherever is its maximum, wherever this particular inversion curve is going to maximum, that is the maximum inversion temperature. Now, let us see that how to derive the expression for the mu Jt. So, for this, what we do, that we start with the not expression but the functionality of enthalpy with respect to pressure and temperature. So, here we find this, we are writing this H is the enthalpy and P is the pressure, T is the temperature. So, we are writing H is equal to some function of pressure and temperature, and then we are using the cycling relationship for state functions. To derive all these expressions, you have to refer to some books on the thermodynamics. So, there you will find all the basic relationships which we are going to use in this derivation. So, here we have the cyclic relationship. We find that it is dou T by dou P at constant H, then dou P by dou H at constant T, then dou H by dou T at constant P is equal to -1. It is very easy to remember that you start with the one pair keeping the other one constant. So, we are doing dou T by dou P at constant H, and then you can take this P in the numerator and this H in the denominator and keep this as constant, and then you take this in the numerator and this in the denominator and take the other one constant. So, this is how we can remember this cyclic relationship, and this is applicable only for the state functions, not the path functions. Now we know that mu Jt is equal to dou T by dou P at constant H. Now, using the cyclic relationship, what we find that we can replace dou T by dou P at constant H by this particular thing, dou H by dou P at constant T and dou T by dou H at constant P. So, from this relationship we are replacing with this. Now, it is simply that we have taken the reciprocal of these two terms. After this, we are writing that dou H, everything we are doing that with respect to H, because H is a function of temperature pressure. So, we are putting everything in terms of dou H by dou T or dou H by dou P. So, for this is remaining same as it is, and this is dou T by dou H by constant P, which we are writing as reciprocal of dou H by dou T at constant pressure. And now, we know that dou H by dou T at constant pressure is the specific heat at constant pressure. So, we can replace this particular term with the Cp. Now, to find this dou H by dou P at constant T, we are again using another thermodynamic relationship, that is Tds equal to dH minus Vdp, and these derivations are given in the thermodynamics book. So, I am not going into those derivations. So, now what we are doing, using this particular expression, we are doing that dou H by dou T at constant T is coming out to be V plus T into dou S by dou P at constant T. Now, there are some Maxwell relationships which are also given in the thermodynamics book. So, from there we find this dou S by dou P at constant T is equal to minus dou V by dou T at constant P. So, what we are doing, that we are replacing this term using the Maxwell relation here. So, we are getting V minus T dou V by dou T at constant P. Now, what we are basically doing here, that we have reduced all the terms in terms of the measurable variables. Okay. So, that is what we have done by this particular thing. Now, here once we have obtained this, we can put this value over here in this expression for mu Jt, and what we get ultimately, we get this particular equation which we showed you earlier in the lecture. So, that is how we can derive the expression for the expansion coefficient at constant enthalpy from the basic thermodynamic relationships. Now, we go to another problem. In this, we have to explain that why an ideal gas would not experience a temperature change upon expansion through an expansion valve. To answer this question, we have to see that what is the value of the mu Jt for the ideal gas, because when mu Jt is equal to 0, it means that on expansion dou T by dou P at constant H is 0. That means on expansion or on compression there is no change in the temperature if it is done at constant enthalpy. So, assuming that constant enthalpy condition, we start with the expression which we have just derived about mu Jt, and we see that if we put this for ideal gas relationship, we put this mu RT by P and we find that this is coming like this. So, here we put the value, we find that this is coming to 0. So, this proves that mu Jt is 0, means it is that there is no change in the temperature on changing the pressure. Now, we come to the another problem. In this, we have to find the Jt coefficient for a gas obeying van der Waals equation of state. Now, let us consider this van der Waals equation of state. So, this is the famous equation of state. In this pressure is getting modified this particular term, and volume is getting modified by this particular term, and perhaps you know that these are accounting for the intermolecular forces and also the finite volume occupied by the molecules or the atoms in the real gas. So, those modifications have been taken into account, and then we are just expanding this expression, and from here what we are doing, we are taking the derivative at constant pressure with respect to the temperature. So, we have derived take the derivative with respect to temperature at constant pressure. So, we get this particular expression, and then we derive this thing. Now, after this what we are doing is that we are going with this, we are just rearranging the equations. This denominator has been taken here and which we are rearranging here, and after this rearrangement what we get, that if you do these rearrangements, you will slowly and slowly get all these expressions, and ultimately you will get this particular expression. Now, after taking this expression, what we are doing, that we have got that this T dou V by dou T at constant P minus V is coming out to be this, and now we are going to the basic definition of mu Jt, and from this we find that we are this particular expression in the bracket has been replaced by this whole expression. Here we can this term and this term get cancelled off. So, we are left with these expressions which we are putting here, and this is how we are able to derive the expression for the mu Jt considering the van der Waals equation of state. Now, please note that this in a similar manner, if you are given some other equation of state for real gases, you can get some other sort expressions for this mu Jt. Now, next problem is this: we are having some unideal gas and some real gas which obeys the van der Waals equation of state, and for that we have been asked to derive the expression for the isentropic expansion coefficient. So far we have looked into the isenthalpic expansion coefficient. Here we are looking at the isentropic expansion coefficient which is there in the expansion engines. Now, for this again we first write the expression for the isentropic expansion coefficient, that is dou T by dou P at constant entropy. Now, here we start with the entropic relationships, that entropy is a function of temperature pressure, and as we did earlier under the isenthalpic expansion, the similar manner we are also taking this expression and we are using the cyclic relationship, and from this we find that the dou T by dou P at constant S is coming out to be this way. And now, what we find that from the thermodynamic relationship again we find that dou S by dou T at constant P is nothing but Cp by temperature, and this dou S by dou P at constant T is this particular expression from the Maxwell relation. Now, this particular then mu S we are replacing in terms of these expressions. So, we find that mu S is coming to T by Cp dou V by dou T at constant pressure. Now, for an ideal gas we know that MPV equal to MRT, and we are getting the value of dou V by dou T at constant pressure, and that is how we are getting this, replacing it with T by Cp V by T. So, we are getting a non-zero value of the isentropic expansion coefficient for an ideal gas, which is unlike the case when we got the isenthalpic expansion coefficient to be 0 for the ideal gas. Now, here what means, it means, as I said in the lecture, that in case of isentropic expansion, even an ideal gas will undergo and temperature change, and because mu s is always positive, so on expansion the ideal gas will always lead to cooling, unlike the case of the isenthalpic expansion when the gas may either get cooled or heated up. The isentropic expansion will always result in cooling. Now, what we do, that we consider the van der Waals equation of state. In this, we write the expression like this, and here what we do again, we take the derivative with respect to temperature at constant pressure, and then we get this expression, and we take this denominator, and now we are rearranging the denominator, and we find that on rearrangement we are getting this particular expression for the right hand side of the isentropic expansion coefficient, and that is how this particular thing leads to this expression for the isentropic expansion coefficient using the van der Waals equation of state. So, in a similar manner, if you are given some other equation of state, then you can make use of the cyclic relationship and the Maxwell relationship, and you can get the expression for the mu s. Now, we go to the next problem. In this problem, what we are doing, that we will seeing these particular things in a TS diagram. Okay, whatever we have learned so far, we shall look into those things again in the TS diagram. So, here we have nitrogen gas having an enthalpy of this particular thing is expanded through an ideal JT valve under the following initial and final conditions. So, here we are given the initial pressure to be this and final pressure to be this, and the initial pressure is this and this. Now, please understand, by changing these pressures, what we are doing, that we shall be having different isenthalpic curves. Okay. So, that is how these two problems would differ, and because we have been specified the nitrogen, the fluid is specified nitrogen. So, we have to make use of the TS diagram or any other thermodynamic diagram for this, and we shall be using here a TS diagram, and we have to determine the temperature in each case. Now, first let us start with the TS diagram of the nitrogen, and this TS diagram you can find in any standard thermodynamics book. Now, we see that here we have this 200 atmosphere isobaric line, and we have the another final pressure is 100 atmosphere. So, we also locate the at this particular isobaric line. So, first we locate these two isobaric lines on the TS diagram, and then we locate this particular enthalpy which has been given in the problem, that is 120 kilojoule per kg. So, from this is the isenthalpic lines here. So, from that we locate this is, you can read, this is 120 kilojoule per kg. So, we locate this particular isenthalpic line. Now, that means both the isobaric lines will be intersecting this isenthalpic line, and as you can see from this particular figure, that both these curves are lying on the left hand side of the maximum of the isenthalpic line. Now, if we simply zoom that particular part, on zooming we can see it much more clearly, that how this isenthalpic line and the two isobars are placed on the TS diagram. Now, we find here that if we take this, that at 200 atmosphere it is intersecting the isenthalpic line at about 117 K. That means, the initial temperature of the gas is 117 K. In similar fashion, we can also find out the gas temperature at the lower pressure, that is 100 atmosphere, and that is coming out to be 119 K. Now, you see that in this case what we are finding, that there is an increase in the temperature due to expansion. So, that means that on this region, so earlier we found it on the PT curve, here we are looking at TS curves. On the TS curve, what we find, on the left hand side of this maximum we are getting the heating, on the right hand side of the expansion we are getting the cooling. So, this difference you must be noting, because depending on the type of the thermodynamic diagram you are using, you may find that the zone of the mu jet less than 0 and 0 may be changing. So, here with respect to the TS diagram, we find that the zone where the mu jet is more than 0 is always on the right hand side of the maximum, whereas the zone where mu jet is less than 0, that is the zone of increasing temperature with decrease in pressure, will be always on the left of the maximum on the isenthalpic curve. So, we find that on the expansion, this nitrogen gas is getting heated up from this 200 atmosphere to 100 atmosphere for this particular enthalpy. Now, again we look into this TS diagram of nitrogen. Now, for the second problem, in the second problem we have been given that the gas is expanded from 20 atmosphere to 10 atmosphere with the same isenthalpic zone. That is, we have to consider this particular isenthalpic line, and we locate these two curves, isobaric curves. One is this 20 atmosphere, and another is the 10 atmosphere. Now, here we can clearly see that on decreasing the pressure, the temperature is decreasing. What it means that if we are changing the inlet pressure, then it has a direct effect on the cooling or heating of the gas and for the same value of the enthalpy. So, value of enthalpy remains the same, but we have simply changed the inlet pressure. So, what we are getting that on zooming we can see that these two temperatures are coming out to be, that is initially at 20 atmosphere it is 116 K, whereas and at 10 atmosphere the temperature is coming down to 103 K. So, this particular thing, as I told you earlier, is leading to the temperature decrease. So, you can find more of these fundamentals from these books. So, first book is on thermodynamics and the rest two books are on the cryogenics, and there you can also find the particular TS diagram which I have referred to. Thank you.